And my talk is about machine learning under changing environment. So as he introduced, I'm an associate professor at Department of Computer Science, Tokyo Institute of Technology. And our university is abbreviated in a different way a long time ago. But now officially we have Tokyo Tech. So don't abbreviate it in a different way. So, and it looks there are several students from our university. And I'm very happy to see they are working here. And I'm personally working on machine learning. And in particular, I'm mostly interested in mathematical part and try to have some efficient algorithms. And hopefully we are recently also working on some practical applications. But this is not really done only by ourselves. So when we do some application, we try to find partners. Otherwise, it's not possible within a small university's lab. And our group at Tokyo Tech consists of approximately 15 people now, 10 students and 5 researchers like them. And about half are actually from abroad, and about half are, of course, Japanese, but they are looking outside. So sad thing is, okay, they are Japanese, but they want to study abroad. So we have some Japanese students, but they are studying abroad. So it's quite difficult for us to maintain those motivated people. And as I said, we have some applications now. And in those cases, often we have some industry partners. And today, so part of the reason why I want to come here is I want to introduce our basic machine learning ideas and wondering whether we could find a good partner also here. So if you have some ideas, let's have a discussion later. And this is my personal standpoint. So my personal goal is to develop an intelligent data processing algorithm that have theoretical performance guarantee. So maybe this is the most important for me. So I'm interested in applications, of course, but I don't just want to do heuristic things. I want to have some algorithm that has theories behind. Of course, sometimes theory and applications are really far, and it's not easy to connect these two. But I think it's nice to have some theoretical flavor behind some practical algorithms. This is my basic idea. And hopefully the developed algorithm is quite useful in practice. And this is also important. I just don't want to work on a single problem, but I want to have a kind of general approach that could be applied to several different areas. And so, okay, so I just wrote a history of my interest. So when I was a kid, I was interested in, okay, computer programming and, okay, computer itself and robots or something like that. But in the university, I started interested in theories. Well, I started working on machine learning when I was a student, and I became interested in theories. And since then, so my interest is slightly becoming toward application direction again. And in the future, perhaps I'm a little bit go more toward applications, but really not really going this way, but somewhere here. So in a sense, my talk will be around in this area, so more theoretical side. But I try to give you some ideas, basic ideas. And if you can get some ideas, then it's nice to have a partner working here. So then we can have nice collaboration. So this is my hope today. Okay, so first let me introduce the simplest machine learning problem. And this is very simple, but in a sense, we are spending most of our life in this simple problem. So given input-output samples, xi and yi, so we have input point here and output point here. So blue dots are given. And given these blue points, we want to learn the rule or function f of x behind the data. So basically, these points are generated following this function, but we have some additional noise here. And what we want to do is to learn this unknown function only from these discrete points. So this is what we want to do. And actually, this simplest problem is a bridge between theory and real world. So I'm working in machine learning, so I think it's a middle, somewhere in the middle here. And in mathematics, there are several good theories like optimization and statistics, algorithmics. And in application areas, we have nice engineering problems like this, and also scientific problems like brain analysis, bioinformatics, chemoinformatics. And machine learning could provide some useful tools in those application and science areas. And I'm looking at this problem from bottom to up and try to provide useful tools in those areas. And these are kind of brief description of challenges and applications of machine learning that we are involved. And the easiest and simplest one would be pattern recognition. Like traditionally, we wanted to do handwriting recognition, and recently images and speeches. And The second one, non-stationarity adaptation. So this is actually the main topic today. So we want to deal with the data that is coming from non-stationary source. Like if we analyze brain activity, so our brain is actually quite non-stationary. Depending on the mood or depending on the person or depending on the time, actually the activity changes a lot. So we have to cope with this change. Otherwise, we can't really learn efficiently. And the second example is robot control. So this is also, we are spending a lot of time these days on working on robot control. And so in robot case, actually, it's not really non-stationary, but robot updates his action or his control policy over time. Then, mathematically, this is actually the same as the fact that the surrounding environment is changing over time. So essentially, mathematically, these two are the same problem. And the third topic is called outlier detection. So this is a simple problem. So we are given a set of bunch of data, and within this data, we want to find some irregular values. For example, if we measure some, say, factory line, then automatically we want to find inferior products. Then, currently, quite a lot of people are really checking the quality of the product by hand. But if this could be done automatically, then this has a strong impact in industry. And another thing is fault diagnosis. Like if we say, so there's a satellite flying, and we can't really measure the behavior of the satellite, but we have some measurement data of the system, and by looking at some time series. And looking at this time series, we want to know whether the satellite is broken or still working well. So this is also a type of outlier detection problem. And the last one is called feature selection. So, for example, like we have some sick patients, and we want to know what the cause for the disease. Like we are given a DNA sequence of the patient, and we want to know which gene is responsible for this disease. And the same thing is also applied to drug discovery. So when we develop some new drug, it consists of several compounds, and we want to know which compound is useful for this purpose or that purpose. And for that purpose, so we are given a set of features, and we want to find the most responsible one automatically. So feature selection technique could be used for this kind of purposes. And they are all accommodated in the same machine learning framework. And in a sense, we try to give a unified framework for solving these set of problems at the same time. Okay, so it's just a brief introduction. And as I said, today I want to focus on machine learning under changing environment. And first, I want to spend 10 or 15 minutes to describe the problem that we want to deal with today. And then introduce the mathematical techniques. Maybe this is just for 10 minutes. And show some applications. And if we have some time, I want to finally cover the latest topic we are working on. And if possible, I want to make things interactive. So if you have some questions, then you can just interrupt me. Then we can have some discussion whenever you want. Okay, so as I said, we focus on supervised learning problem. And let's consider a simple age prediction problem. So we have input X and output Y. And X is an image, like let's say this bar. Say image is now 16 by 16. So then we have basically 256 dimensional vector. So we just align the 2D image into 1D vector. So then X is a 256 dimensional vector. So they are face images. And output Y is the age, like he is, 30, or he is 40, or something like that. And given some samples, Xi and Yi, we want to learn the input-output rule behind them. So given the image, the function returns the age of the face. And then if we can learn a function f hat successfully, we can predict output of unseen test inputs. So for training, of course, we know the age of these people. But in practice, we want to predict unseen test images. And in machine learning terminology, we call this fact generalization. The learned machine can generalize to unknown situation. So it's called generalization. And this is the main topic, main interest in machine learning. Okay, here's a question. So we have a person here. And we want to predict the age of this person. Maybe Kenichi had a training session half a year already. And perhaps you should know the answer of this one.
I don't know actually. I guess many of them don't know.
Does everybody know that? I just looked at it at Wiki yesterday.
Okay.
So he's 53. So anyway, so we want to do this kind of thing in this case. And okay, this is just an example. The problem we are discussing is just a general function approximation problem. But you may have an image like this. So the problem is something like this. And okay, it was a supervised learning problem. And in this supervised learning problem, we always make a strong assumption behind. So it's like this. Training and test samples are drawn from the same probability distribution. So basically, we assume that images are coming from some probability distribution and drawn randomly. And in this process, we have to actually assume that training X and Y and test X and Y are coming from the same rule. And okay, these two are coming from the same rule. So that's why we can predict something about the test data from training data. In a sense, this is an essential assumption. But my question here is this assumption really true in practice? And of course, my answer should be no here. Otherwise, my talk finishes here. So it's not always true. Of course, sometimes it is possible. It is true, but it's not always true. And I want to show some examples. So let's focus on the face again. And it's called sample selection bias. So training samples are usually gathered within the lab. And as I look at here, so we have all men here. And okay, this is a famous data set. And if we see that, okay, only one lady here and others are all men. So this is maybe the truth in most of the research lab, unfortunately. But in the test case, so we want to use the face recognition system, not in the research lab, but outside the lab. Then maybe the men-women ratio is almost 50-50. So already the distribution of the sample is different. This means this assumption is not satisfied anymore. So I think face recognition is already a quite common, popular technique. But actually, this is really a difficult problem because this basic assumption is not fulfilled. So that means if we just naively use the standard technique, then our solution is not reliable. Well, we don't have any theory behind that. So that's one thing. And another example is learning from questionnaire. So, okay, the example is, okay, I'm giving a lecture at the university, and at the end of the lecture, students were asked to have some questionnaire, whether he was interested in this lecture or he liked it or not. And he evaluated my course. And usually, training samples are quite dominated by extreme opinions. Okay, this is my hope. So from 1 star to 5 star. And maybe most of the students think my course is okay, it's not excellent, not so poor, but maybe average. So I think the distribution would be something like this. But if we take the questionnaire, then those people here are not really interested in answering to the questionnaire. It's just a waste of time. So they don't care. They are not interested. But if some students don't like my course very strongly, or if they really like my course, then they want to actively answer to the questionnaire. So then basically, we only have samples from here, and not from here. But of course, the reality is this distribution. So this already means that training and testing have different distribution. And this sample selection bias issue is really common in many situations. But if p-train and p-test are totally different functions, then we can't do anything. We can't learn anything about test points from training points. So that means we need some reasonable assumption. So p-train and p-test should be related in some sense. And there are a lot of possibilities. And later, if we have some time, I want to introduce some other ideas. But here we focus on the simple case called covariate shift. And covariate is another name of input in statistics. So it could be just input distribution shift, but covariate shift sounds a bit fancier. So we want to use this one. And in covariate shift, input distribution changes. So p-train x is different from p-test x. But the functional relation, like y given x, so this is the probability of y given x. So it's essentially a function. So this function is the same, but input distribution is different. So this is called covariate shift. And we want to work on this problem. We want to explain this problem today. And here's a simple example. So let's fix a function f of x like this. And p train x is this one. And p test x is this black one. So then basically training points are coming from the left-hand side. And the testing points are coming from right-hand side. So we have points here for training. And from these blue points, we want to make a prediction of these black crosses. So it's called an extrapolation problem. We want to make a prediction outside the training region. So it's really a hard problem. So the covariate shift phenomenon covers this extrapolation problem. And we have some nice theory for this extrapolation problem. And we show some examples of covariate shift. So one is called brain-computer interface. So this is the joint work with Technical University Berlin. And we have been working together for already 7 years or so. And they are seriously working on brain-computer interface. And we are seriously working on machine learning theory. And we combined these two ideas and had some practical results. And the purpose of BCI is to control computers by brain signals. So usually we use keyboard or mouse. But here we don't want to use that. We just imagine, okay, move right or move left. Then the cursor moves. So this is what we want to do. And more specifically, we use EEG signals of our brain. So we put some electrodes on our scalp and measure the brain signals, EEG signals. And output is either, for simplicity, either left or right. And okay, here's a small movie. So it's a training phase. So first we need to have training samples. And on the screen, we have some instruction, just L or R. If it's L, then we imagine left hand movement. We don't move left hand, but he is imagining moving left hand. So then actually our motor cortex corresponding to the left hand is activated. And this is recorded as a training sample. And if it's R, we imagine right hand movement. Then motor cortex corresponding to the right hand is activated. And this is recorded. And we gather maybe 120 samples or something like that for 5 minutes or 10 minutes. And then use these points as training samples. And then in the test phase, where we can control computers by brain signals. So here we use some games. Maybe, so as I see the ages, so you know the game Pong, the simplest game. You just control the pad to left or right. So he is really imagining left or right. Control. And the cool thing about this movie is that, so there's another pad here and another screen here. And actually there's another person sitting here with the same head cap. And they are really playing games together in the room. It's very strange. They are quiet and they are really but they are working really hard now. I have also done some experiments by myself, and it's really actually interesting because you can really move the cursor as you wish in many cases. But actually it's quite tiring, so we have to really concentrate, and I had some muscle pain later.
I have a question. So
yeah.
His head was fixed to the chair, or just he?
No, he can move.
Concentrated.
Yeah, he's concentrated, and this is our assumption. So if we allow them to move their heads or like eyebrows, then we can record some electric signals. Then it's easy. So we ask them to not to move at all, but just imagine hand movement.
Yeah, I admire him.
So accuracy is not so high. So in principle, we want the paralyzed person to use computers. This is the ultimate goal. But maybe that's not so easy, or that's not so realistic, because some patients can move somewhere, like only eyebrows or finger. Then we could use this one as a user interface. So this is more like an entertainment purposes, I think. But it's quite fun and I think useful. Okay, anyway, so it's like that. So this is one example. And what was non-stationarity in this brain-computer interface? As I said, so different mental conditions or different mood causes variations in EEG signals. Like in the training phase, as you can see, it's quite boring and sleepy. And actually, I once felt asleep when in the training phase. And it could be easily recorded, and the person next to me just point out, "Oh, don't sleep." So it's really hard. And on the other hand, in test phase, it's fun and exciting. So our mental condition is totally different. And this shows some difference between the training and testing phases. And clearly, the brain activity is very different. So we have a distribution shift in the training and test phases. And the last example is robot control by reinforcement learning. So the purpose is to let the robot learn how to autonomously move without explicit supervision. So we used actually a simulator, but our simulator simulates this robot called Kepler robot. It has 8 infrared sensors. So it has infrared sensors, and it can measure the distance to the wall. By that, he can know where he is. And it has 2 wheels here and here, and it can move. Then by that, he can go straight and go back, or rotation left or right. And we want the robot to go through the maze like this, without explicit supervision. This is what we want to do.
Does it have a GPS?
No, so it only measures the relative distance to the wall. So if he knows the GPS, he has the GPS, then things are much easier. Okay, and we want the robot move autonomously, and this is almost equivalent to going forward without hitting the wall. So we first believe this one. Then next thing we do is to give the robot rewards. Maybe robot just move randomly in the beginning, and if he can go forward successfully, then we give him a positive reward. And if he accidentally hit the wall, then we give him a negative reward. And within this formulation, we just ask the robot to earn as much reward as possible. Then robot try to gain more positive rewards. And as a result, he can go forward without hitting the wall. So this is what we expect him. And I have some small cartoon here. And this is actually related to the current context. So like if you have a baby, and if the baby does some job quite well, then the parent praise him. Oh, you did a good job. So this is actually a positive reward, and he feel happy. Then he tries to repeat that action again. On the other hand, if he make a mistake, then maybe the parents scold him. Then he doesn't want to do that again. So it's really the same as the robot learning. So in a sense, we want to imitate this learning procedure in the robot framework. And that's actually a rather simple problem in mathematics. And we have a small result like this. So after learning, we didn't teach anything to the robot, but just give a positive reward when it goes forward, and give negative reward if he hits the wall. Then only by that, after several iterations, the robot can really avoid the obstacles smoothly.
I have a question.
Yes.
What is the relationship with the changing environment?
Okay, so that's coming actually next. So it looks nothing related to the changing environment, but actually it does. And as I said, in this case, the surrounding environment is not changed, but the robot itself is changed, updated. And in this kind of learning process, we often use the method called policy iteration. So it's quite simple. In one step, we evaluate the current control policy, whether how good the current control policy is. And then in another step, based on this evaluation, we improve the control policy to gain more reward. And just repeat these two. And if the robot updates his own control policy, then this actually changes the input distribution. Basically, we are learning the function between the current robot states and reward, the relation between these two. And if the robot changes the control policy, then the distribution of the states actually changes. So this naturally causes covariate shift. And mathematically, this is really exactly covariate shift. Did it answer to your question?
Yes, but what is the purpose of the robot control? Does the robot have goal position or just go?
So in this case, just go around and just don't hit the wall and go forward.
Just patrolling.
Right. Exploring the environment. And I didn't explain the detail, but essentially we are learning the function between reward, between current state and reward. And the state is an input. And if we update the robot's control policy, then the distribution of the states changes.
So, in the movie,
Yeah.
robot can go to avoiding that.
Yeah.
But
Mm.
so in some environment, robot can turn around by mistake. But
By mistake means does it hit the wall? No?
I think
Yeah, so that could be possible. So there might be some local optima. But,
but question is, I think the environment is very easy to solve the problem. So
Yeah, but I think in this case, the environment, you can think of the environment depends on what the robot sees, observes.
Yes.
I mean, so for example, in this case, maybe the robot can learn if the robot sees something in the front of him, just turn left.
Yes.
And actually, that rule will work for the first two turns.
Yes.
Right? Yeah, but maybe he's happy. But at the third turn, if the robot turns left, he sees the wall again, and maybe he hit the wall. So I think what the robot can see is just in a very close environment.
right.
And if robot changes their policy, maybe the robot will see a totally different environment. I mean, the unobserved environment. So I think in this sense, the situation on the environment changed.
Yes, I know. But I think is yes, I know.
Do you want to discuss this later?
So maybe I didn't really get the point yet. So maybe we can have some chat offline later. Okay, so anyway, this reinforcement learning is also one of the examples of covariate shift. And if we can have a general theory for coping with covariate shift, then we can apply that to either brain-computer interface or robot control. And we did both already. Okay, now it's main part. We have some mathematical part. I try to avoid some messy part. Just I want to convey the main idea to you. And for illustration purposes, let's focus on a linear extrapolation problem like this. So there's a true function f of x here, red one. And we have training points, blue ones, and test points. So these test points are not given, but in the future we are given that. And we want to make a prediction for these guys. And we want to approximate the function only using a straight line function like this green one. So it's called linear extrapolation. And for this kind of setting, the simplest method is ordinary least squares. Maybe you are familiar with that. So we just want to fit the current function to the point, blue point. So given blue points, we want to fit the function to these blue points. So this is what the least squares does. And in standard setting, without covariate shift, this ordinary least squares is actually said to be consistent. So consistent means the learned function, green one, converges to the optimal solution when the number of samples n goes to infinity. So this is a very important property for statisticians. So if we have many points, then our solution is guaranteed to be optimal. So this is the kind of necessary condition for us. So this is a nice property. But under covariate shift, unfortunately, this ordinary least squares is no longer consistent. So it converges to somewhere else. And actually, we have, in the future, we have testing points here. So that means the function we want to have is like this. It has positive slope like this. But we have a function like this one, green one. And this green function is already almost converged to some point. So this is totally different from what we want to have here. So this already illustrates the failure of ordinary least squares under covariate shift. And okay, here's a small theory. So it's called the law of large numbers. So it's elementary statistics. So we often take sample averages. Like given we have a function a, and we have training points, and we just take the average over n training points. And if the number n goes to infinity, then this converges to the expectation. This is actually integral over p train x. So this is the true population mean. And the law of large numbers guarantees that this always converges to this one. Okay, this is the standard one. But in the current setting, what we want to do is to estimate the expectation over test input points like this. So this is p-test, not p-train. But we are allowed to only use training input points. So xi are coming from p-train. So samples are from p-train, but we want to predict the expectation over p-test. So these two are different. So we have to do some adaptation. Otherwise, the solution converges to somewhere else. And here's a simple trick. It's called importance weights. And the importance is the ratio of test and training input densities, like this, p-test over p-train. And the idea is quite simple. We take the importance weighted average. Instead of just taking the average of A, but we have importance weight here. And again, xi are coming from p-train. So then, by the law of large numbers, so now we think this entire part is one function. Then the law of large numbers said, so we have this function here, and expected over p-train, like this. And then, okay, here's p-train and here's p-train, and these two are cancelled to each other. And in the end, we have expectation over p-test. So by applying the importance weight, we can somehow convert the training points into test points. Asymptotically, we say asymptotically if the number of samples is infinitely many. So this is the basic technique. And in practice, we have to need more practical extension of this idea. But basically, we use this importance weight for adaptation. And the simplest idea is just importance weighted least squares. So instead of just least squares, we have importance weight here. And this is just quite naive. But surprisingly, we have a function like this. So we are only given blue points, and we only use blue points. But we have green function like this. And clearly, this green function predicts black crosses better than the previous examples here. So this importance weight actually works really well in this kind of setting. But of course, we have to estimate the importance weight itself. So in theory, we just assume this is given. But in practice, we also have to estimate the importance weight. So this is the next target we have to discuss. And I just want to give you a brief idea for importance estimation. And the setup is as follows. We are given training input samples from training distribution, and test input samples from test distribution. And a naive approach would be to just estimate p-train x and p-test x from these samples separately. And then we have now estimate of p-test and estimate of p-train. Then just take the ratio of the estimated densities. And in principle, this can solve the problem. But unfortunately, in the machine learning community or statistics community, it is said that density estimation is too erroneous, and it contains a lot of errors, and we shouldn't do density estimation. And we have a bit more systematic principle. It's called Vapnik's principle. If you are familiar with machine learning, perhaps you have ever heard of the method called support vector machines. So Vapnik is the person who developed support vector machines. And he said this kind of principle. So when solving a problem, more difficult problems shouldn't be solved. So that means when we solve one problem, often we want to climb higher than this problem and then going down. If we do that, then we spend too much energy to get to the top intermediate, and we lose something in the end. And support vector machine actually follows this principle, and it is shown to be one of the most powerful algorithms in machine learning areas. And here we want to apply this principle in the density ratio framework. Okay, now suppose we know p-train and p-test, two densities. Then we can easily compute its ratio, just taking the ratio. But if we know the ratio, only know the ratio, we can't really decompose this one into p-train and p-test. This decomposition is not unique. So this implies that solving the left problem is actually more difficult than the right problem. So if we do density estimation like this, then actually we are solving more difficult problem than knowing the ratio. So this means we should estimate the density ratio directly without going through density estimation. So this is what we want to do. And I just briefly describe the method. So now we define the ratio as W of X. And we try to learn this W directly without estimating these two separately. And we use a linear parametric model for learning this function. So we have some basis functions like Gaussian functions or polynomial or whatever, some fixed basis functions. And we have parameters here. So basically the learned function is a linear combination of some parameters. And so if we have an estimate W hat, then the test input density can be approximated like this. So W corresponds to this ratio. So if we multiplied this with P train, we have P test here. And based on that, we use the standard statistics technique called maximum likelihood estimation. So this is formulated like this. Basically, we have a simple objective function to maximize like this. And also, so this P hat test should be a probability density function. So we need this kind of constraint. So this part is a bit technical. And we also need to guarantee the non-negativity like this. And then, so in the end, we want to solve this optimization problem. And good news is that this optimization problem is called convex. So convex means there exists only one solution, and it can be easily obtained. So that means the equation itself is a bit complicated, but we can efficiently obtain the unique optimal solution. And furthermore, we can show that the solution becomes sparse. Sparse means, so the learned parameter is now theta 1 to theta t, but sparse means most of theta t's are zero, theta i's are 0. So some are non-negative and others are 0. So this means our model is a linear combination of prefixed basis functions, but we don't really have to take the summation over all basis functions, but only a few with non-zero coefficients. So this is very useful in practice when t is very large. Then we don't have to repeat. If t is 1 million, usually we have to repeat 1 million times. But if it's sparse, it could be only like 1%, or sometimes even less than that. Okay, that's the basic techniques. And of course, behind we have more mathematical things. But the basic idea is to apply the importance weight. Then, so environmental change could be adapted. And also, we now have a method to directly estimate the importance ratio. So we apply those techniques in BCI again. Yes?
More into the application, I have a question
yes.
about the convergence speed of importance weight squared.
So
intuitively, I guess the convergence can be very slow in the importance weight introduced.
Yeah, that's a very good point, actually. Thank you very much. So our prediction error could be decomposed into two terms. One is called the bias, and the other is called the variance. And theoretically, we want to minimize both of them. And if we use ordinary least squares, then bias is actually quite large, but variance is smaller. And on the other hand, if we use importance-weighted least squares, then bias becomes quite small, but variance becomes larger. So as you said, the convergence speed could be slower. So this is actually the basic technique. And in practice, we have to have more stabilization part. Like we have regularizer here, where we may slightly flatten the importance weight. If it's all 1, it reduces to the original ordinary least squares. So we may slightly flatten the importance weight. By that, we can actually optimally control the trade-off between bias and variance. And we also have a nice model selection technique for that. So this is not covered today, but we have some theory for that also. Thank you very much. Any other questions regarding this? Okay, so we had some technique, and we want to apply that. So already I have shown some demo, so here it's only number. So using the existing techniques, the correct prediction rate of left to right class was something like this. But if we apply the importance weighting techniques, it could be improved a little bit. So this time, unfortunately, the performance was not so significantly improved because in the case of BCI, the distribution change is not really covariate shift, but it could be whatever change. So if we really see the data, it's very noisy and dirty. So often P-train and P-test looks nothing related to each other. But in that case, we can't learn anything. But still, we believe that some kind of covariate shift is included in the data and just applied. But still, we have some performance gain for some cases. So that means even if the assumption is not perfectly fulfilled, still we can apply our techniques in some real problems. This is one thing. And also, we did a similar experiments for robot control. So this time we use a different robot. It's a small cart like this. And pendulum is hanged here. And if we move the cart to left or right, then the pendulum moves. And the task is we want to swing up the pendulum and keep it to the top by balancing it. So this is really a hard problem. And we apply the covariate shift adaptation techniques. And then, so the horizontal axis is the time, and the vertical axis is a kind of success rate kind of thing. And then existing method does not really improve the performance in the later stage. This is due to the shift in the data distribution. But in our case, we have adaptation techniques. Then performance gets better and better. And this is actually almost the optimal solution here. So it converges to the optimal solution.
I think
yes?
It's a traditional program for
it's a traditional, yeah.
In reinforcement learning. So I think I think currently we have a lot of techniques to achieve such an optimal strategy.
Yeah, so I don't deny that, but here we actually make the problem very difficult. Like the number of samples is very small, for example. And we want to show that, so with or without adaptation, whether we can improve the performance or not. So this is actually the main issue. Maybe the problem is maybe traditional and simple. So if you have more sophisticated techniques, we could achieve that.
I think you should try, in Japanese, Nidan pendulum. So
yeah, actually, we also have a similar experiments for more complicated one. But today, unfortunately, it's not included. So if the problem gets right, so in a sense, we are as I said in the beginning, we are on the theoretical side. So we just want to illustrate whether adaptation technique is really useful or not. And if we are really on the application side, then we should, of course, use more complex and realistic robots. And perhaps we should find a good partner to really do that. Anyway, for this simple problem, our method was better than this one. And here's a small movie. So what we could do is only simulation within our lab. So it's something like this. So actually, in the end, the robot keeps the pendulum to the vertical position. But this itself is also quite difficult. So it looks the robot just moves left in the end. But it's not, he's actually really controlling the balance every, 0.1 second or something like that. So the control problem is still not so easy in this case.
Did you try to add noise?
Yeah, already noise is included here. But of course, if the noise level is very high, then none of the method works. So, yeah.
How about limitations for left and right margin, like end of the track?
That's a very good question. So in this case, our state is only the angle of the pendulum. So we didn't take the position of the robot into account. So that means we assume that there's no boundary. But if there's a boundary, then we should have the position of the robot as a state. Otherwise, it's not a solvable problem. But our robot doesn't have a GPS, so it cannot measure the position exactly. But if we have that, then we could also incorporate that theoretically. That's a good point. Okay, so I still have 10 minutes. So finally, I want to briefly explain what we are doing. Today, we focused on the problem of covariate shift, so distribution of X input changes. But we may consider other types of distribution change, like class prior probability change. So in this case, the P of Y changes. Maybe this is really the man-women ratio change. In the training phase, P train, so men is only 10% and women is 90%, and women are 90%, and the test phase 50-50, something like that. And another one is called mixture ratio change. Perhaps Kenichi had worked on a slightly related framework. It's more like a generative framework. So we know the shape of the P train, and also the shape of the p-test. We have some parametric form. Or maybe this part could be P1, P2 could be non-parametric, but we have some parametric form for alpha. And we assume that these two are the same, but the mixing ratio changes. it looks people in NLP are also working on this kind of model. And personally, I didn't really go into this mixture ratio change, but I think we can, in principle, apply a similar technique to solving these problems, these settings at the same time. Okay, and related issue. As I said, there must be several distribution changes, several types of distribution changes. And if we know the model of the distribution change, then we could prepare a suitable adaptation technique. But in reality, perhaps we don't know anything. We just have data. Maybe something is changed. So in practice, first we have to detect whether distribution change occurred or not. And we already have a nice theoretical techniques for achieving the first goal. But the second problem is still open. So how to classify the type of distribution change? Now we know distributions are different, but we want to classify whether it's covariate shift or class barrier change or some other general change. So this is still an open problem for us, and we are working on that now. And in the current setting, we assume that we only have test input points. But in some cases, we can also have some test output values. Not many, but maybe a few could be available. And in such a situation, actually, we could do more. We could further improve the performance. And this kind of setting has been studied by the name of transfer learning, or domain adaptation, or inductive transfer. Also, multitask learning are the same kind of thing. So, in a sense, our framework could be made more general by taking into account the test output values. But this is also still an ongoing work. And, okay, this is really what we are doing that. So, in adaptation techniques, we used importance weight, the ratio of two densities. But recently, we found out that this density ratio could be actually used for various data processing purposes, not only for adaptation, non-seasonality adaptation, but for other purposes, like outlier detection or feature selection we introduced in the beginning, and also some other statistical machine learning problems. So that means once we can estimate the density ratio accurately, then we can solve these interesting problems at the same time within the same framework. This is what we are currently working. And I just want to briefly explain the first two problems, outlier detection and feature selection. And the goal of outlier detection is, as I said in the beginning, to identify irregular samples in the data set. So for example, detection of inferior products in assembly line. In the assembly line, some products are made every 1 second. And we have some measurement data for each product. And at some point, maybe some inferior products are included, and we want to automatically identify that. Or like fault diagnosis of some remote robots like satellite. And outliers detection is actually a hard problem because samples with low probability densities are usually regarded as outliers. If you have a distribution like this, outlier actually lies here. So we have small peak here, but it's not really visible. So it's really hard to detect. But once we use the density ratio framework, then this could be made milder. But assumption is we have a set of samples that are all regular, non-outlier. So we have kind of regular distribution, or samples coming from the regular distribution. And we have some set of samples that may contain outlier, and take the ratio of these two. Then outlier part is really emphasized like this. Then by that, we can easily detect outliers. So this is one fruitful use of density ratio framework. And the last one is called feature selection. So we have vector input, like d-dimensional vector like this. And output is a scalar y. And the goal is to find the input variable xi that is the most responsible for explaining output value y. So as I said, its example includes gene selection. So we want to explain which gene is responsible for this disease, or which compound is responsible for this effect of the drug, or something like that. So this kind of feature selection is often used in science purposes, but I think there must be some engineering applications also. And some small mathematical details is here. So for feature selection, we use the quantity called mutual information. It's a popular quantity in information theory. So it's defined like this. And okay, it's a bit complicated, but if mutual information is 0, then X and Y, so this is mutual information, and this is 0, then X and Y are independent statistically, nothing related to each other. So this means X does not contain any information on Y. So then we just compute the mutual information between Xi and Y for all Y, and choose the one that has the largest mutual information, the smallest mutual information. By that, we can detect the most informative feature or most less useful feature like that. And clearly, so mutual information contains density ratio here, so we can still apply the same technique.
Isn't it just a sufficient condition?
Okay, so first one is necessary and sufficient. Mutual information is 0, then this is X and Y are independent, and vice versa. But this is maybe a bit informal. So these two are equivalent. Okay. And finally, so I just make a small advertisement. This is put on YouTube. So in the very near future, we're going to have a book on this distribution change. Now we called it covariate shift today, but now it is more generally called data set shift. So it contains whatever change between training and testing. And 2 or 3 years ago, we had a workshop at a conference called NIPS. And this is a kind of workshop series of the book, but we have several interesting articles on data set shift. And this is coming, I think, quite soon from MIT Press. And the second one is robotics book. So Hachiya is actually our student in our lab. And we are writing, so this is a Japanese book, but we have a kind of very basic textbook for learning robot control by reinforcement learning. Okay, so this is the last slide. So in this talk, I introduced the supervised machine learning framework. Given input-output samples, we want to learn the rule behind them. So this is the goal. And we introduced a phenomenon called covariate shift. So input distribution vary between training and testing phases, but the functional relation, the function does not change over time. And so our non-stationarity was kind of one step, training and testing, but this could be made multi-step. So by that, we can really track, pursue the continuous distribution change. So we just focus on one step, but if we just shift, then we can basically apply the same technique to continuous distribution change. And we have actually already done that in reinforcement learning framework. And the key of the adaptation technique, maybe this could be a take-home message, importance weighting. So this is the technique we used. And this importance weighting technique could be applied in like brain-computer interface, robot control. And we are also doing more experiments now. And finally, I showed that the density ratio itself could be a new versatile tool in statistical data processing. And currently, we are working on several problems, and we really want to show that density ratio could be a kind of new framework for statistical machine learning. Okay, thank you very much.
We still have a couple minutes. Any question?
So your presentation mainly about the continuous, not so high-dimensional input space, I think. So is there any case someone tried applied these techniques into the high-dimensional discrete?
We are doing we are doing that, but still we didn't have a really very promising result yet. But still it's continuous. So continuous high-dimensional space is our interest, but discrete could be a bit more difficult.
Do you see any big difference between the discrete space?
Yes, because in the continuous case, we can assume the continuity or smoothness of the function, but in the discrete case, it's not. So it's really harder.
And I have one more question.
Yes.
So I think the density ratio can be applied to the active learning.
Right. Actually, we already have several papers on active learning. And honestly, we have started from active learning. And then we found that so this could be used in more different purposes. Yeah, good point. Any other questions?
No more? Okay, thanks, speaker.
Okay, thank you very much.